This is Lab 5, the world's largest rope swing. In this lab, I observed and analyzed the jumper's motion in the viral video, The World's Largest Rope Swing, using known physical quantities and computational modeling. Other objectives in this lab included creating two computational models in VPython that include drag and no drag interacting with the system, comparing the predicted motion in both models, plotting the energy changes associated with each model, and questioning the validity of my models as they relate to the energy principle. In addition, I used the momentum principle to calculate all the forces acting on the system while iteratively predicting the system's motion, and I utilized the energy principle to calculate the energy changes associated with the system. Lastly, it was deduced that both models satisfied the energy principle and the drag model was a more realistic prediction for the jumper's motion. As stated earlier, I used the momentum and energy principle for this lab. From lecture, we learned that we can manipulate the momentum principle shown above to obtain the velocity and position update equations as shown to the left. Additionally, we learned that the energy principle asserts that the change in energy is equal to the work done on the system by the surroundings, and it states that energy cannot be created nor destroyed. This principle is useful because it will help me to analyze the multi-particle system and calculate its change in energy by taking the sum of the kinetic energy and the change in gravitational and spring potential energies, all of whose formulas are shown below. The image to the left displays how potential energy arises from the interaction of a pair of objects similar to that in this lab. Before beginning the lab, however, I identified the system and other physical concepts that related to the lab. As you can see to the left is an image of a jumper swinging around corona arch very much like that of a pendulum. The system was the rope, the jumper, and the earth. The forces interacting with the system included the gravitational force and the spring force, since the rope behaved similar to that of a spring. Lastly, the energy variation involved was the system's kinetic energy and the spring and gravitational potential energies. After watching the behind-the-scenes video, I was able to obtain several initial conditions and values. Once again, the video states that the jumper moves like a pendulum as pictured to the bottom right, and I also learned that the rope length was 45.72 meters. The jumper's distance from the ground when the rope is fully stretched is 3.048 meters, and the spring constant was 30,000 newtons per meter. To obtain my initial conditions, such as the jumper's mass and drag constant, I researched these values using engineeringtoolbox.com and found that the average mass of a person is 70 kilograms, and the drag coefficient of an upright person is pictured below. The drag constant used, however, was the average between 1 and 1.3, which was 1.15. The model for this lab is shown to the left and includes all the information discussed, with the ball of mass representing the jumper and the top ceiling representing the top of corona arch that they are jumping from. To create the computational model without drag, I set the initial position to start from 45.72 meters to the left of the origin along the x-axis, because this is where the jumper will begin their jump, and their velocity initially is 0 meters per second because they start at rest. We will start the model at t equals 0 and advance about 1/210 seconds. Below in blue, I defined the spring stiffness and relaxed length as stated previously, and I defined the gravitational constant to be 9.8 newtons per kilogram. In green, I used Hooke's law to calculate L hat and the spring stretch, and lastly, I incorporated the energy principle to calculate the kinetic energy and the spring and gravitational potential energies to calculate the system's total energy. Next, I updated the system's data iteratively by defining my initial energies, calculating the spring and gravitational forces in blue, incorporating the use of the momentum principle to update the velocity and system's position as well. In purple, I used Hooke's law once again to update the spring stretch, and lastly, I used the energy principle to update the system's energy as shown in gray by taking the sum of delta K, delta UG, and delta US. For the model including drag, the same initial conditions and iteration process was the same, except that we included a proportionality constant 1.15 and calculated this drag force and factored this as an additional force to calculate a new net force acting on the system. These additions are shown in blue. After running both models, we can see that the model without drag is on the left and the other including drag is on the right. Notice that in the model without drag, the jumper completes the oscillation and reaches the peak height, returning back to the initial position. However, in the model with drag, the jumper does not complete the oscillation due to the drag force decreasing the velocity and kinetic energy, so the jumper does not reach the initial position. This model is more accurate in displaying motion in real life, however. Also, the red arrow represents the spring force from the rope, and the black arrow represents the gravitational force acting on the system. Additionally, the graphs are produced from both models. These graphs display the change in energy versus time, with the kinetic energy being highlighted in blue, the gravitational potential energy in red, the spring potential energy in green, and the change in energy in orange. Notice how the model without drag at the top has a symmetrical yet different phased energies, and the amplitude is equal in each period. Also notice how the model with drag has varying energies and how kinetic energy decreases, which makes sense due to the drag force. and how the change in energy eventually zeroes out in both. With this information, we can now answer the main question, which asks if the energy principle is obeyed in the two models. The energy principle is obeyed here because the change in energy is zero and the energies associated with the system follow the principle's conservation of energy, such as how the kinetic energy and gravitational potential energies are inversely proportional and not being created or destroyed. In conclusion, by using the momentum and energy principle, I observed the jumper and created a computational model of the motion and calculated its change in energy with and without drag. This is also significant because it also allows us to understand everyday phenomenon and relate these events or actions to the physics we have learned in this course. Thank you for watching.